Now let us see some of the properties of random variables having the same distribution. So let x be a random variable with probability mass function or probability density function fx, and suppose capital Fx is the distribution function of x, and suppose mu is a fixed point in R. Now if fx mu minus x is same as fx plus mu plus x for every x belonging to R, then the distribution of x is symmetric about mu. So if we try to look at this in case of PDF, suppose this is the PDF, what it says is mu is over here, mu plus x may be over here, mu minus x would be here. So the two are same. So what it says is this condition, if your PDF or probability mass function is such that the curve on the right hand side of mu is a mirror image of the curve on the left hand side, then the distribution of x is symmetric about mu. So you see that is what is happening over here. The curve on the right hand side is a mirror image of the curve on the left hand side. Then second part says distribution of x is symmetric about mu if and only if fx mu plus x plus fx mu minus x minus is 1. Third result says distribution of x is symmetric about mu if and only if the distribution of y is equal to x minus mu is symmetric about 0, which is straightforward to prove just using the definition. This is very important result. If distribution of x is symmetric about mu and expected value of x exists, then the point of symmetry, which is mu, has to be the mean. It's a very important result which says that if a distribution has symmetric distribution, then the point of symmetry has to be the mean. Then if the distribution of x is symmetric about mu, then fx mu minus would always be less than or equal to half, would always be less than or equal to fx mu. So that means if fx was continuous at mu, then fx mu has to be same as half, because then fx mu minus would be same as fx mu. So that means fx mu is same as half, which is same as saying that probability that x less than or equal to mu is half, which is same as probability that x greater than mu. So in a sense what it says is mu is also a point which divides the whole probability density function or whole probability mass into two equal parts, such that probability x less than or equal to mu is half and probability x greater than mu is also half. Then this result says if distribution of x is symmetric about mu, then all order movements around mean would be 0. So these are all order movements about the point of symmetry, they would be 0, provided the expectations exist. Let us try to prove one by one these results. These are not difficult to prove. So in the first case, let us take y1 is equal to x minus mu and y2 is equal to x minus mu. What is given to you is fx mu plus x is same as fx mu minus x for every x. So I look at the density of y1 is equal to x minus mu, which is same as in the discrete case. For example, it would be probability that y1 is equal to y. Probability y1 is equal to y is same as probability that x equal to mu plus y, which is same as probability mass function of x at the point mu plus y. What would be probability y2 is equal to y, fy2y? So probability y2 is equal to y is same as this is equal to y, which is same as probability that x equal to mu plus y. Sorry, I'll have to take y2 as mu minus x, because I have to show that y1 has the same distribution as y2. To show that x has a symmetric distribution about mu, I have to show that x minus mu has the same distribution as mu minus x. So probability y2 is equal to y would be same as probability that x equal to mu minus y, which is fx mu minus y. So what I get is f1y is same as, now this is given to you, so that is why they would be same. So what you get is fy1y is same as fy2y for every y belonging to R, which implies that y1 has same distribution as y2 by a result which we did earlier, which says that if probability mass functions are same, then the random variables will have the same distribution. Now in this case I am given that x minus mu has the same distribution as mu minus x in the part B. Part B says if x and b, if x has a distribution symmetric about mu, if and only if this happens. So that is what I am trying to prove now. So X has distribution symmetric about mu if this happens, which is equivalent to saying that distribution function of this is same as the distribution function of this, which is same as probability x minus mu less than or equal to x is same as probability mu minus x less than or equal to x. Let us try to write down this probability. This is same as probability x less than or equal to mu plus x. What is this probability? This is same as probability x greater than or equal to mu minus x. Now what I do is I write down probability x greater than or equal to mu minus x as 1 minus probability x less than mu minus x, which is nothing but 1 minus fx mu minus x left hand point, left hand limit at the point mu minus x. If I put this quantity is equal to this goes on this side, so this is fx mu plus x plus fx mu minus x minus is same as 1. Let us try to prove the C part, which says distribution of x is symmetric about mu if and only if the distribution of y1 is symmetric about 0. So distribution of x is symmetric about mu if and only if this happens, which is equivalent to saying that x minus mu has same distribution as minus of x minus mu, which is equivalent to saying that x minus mu is same as y1, so y1 minus 0 has the same distribution as 0 minus x minus mu is y1, so it is minus y1, so 0 minus. So what you conclude is y1 minus 0 has the same distribution as 0 minus y1, which is equivalent to saying that y1 has same distribution as minus y1. So x has a distribution symmetric about mu if and only y1, which is this x minus mu, has a distribution symmetric about 0. Now let us do the next part, which says that if distribution of x is symmetric about mu, then the point of symmetry has to be the mu, provided expected value of x exists. Now note that x has a distribution symmetric about mu if and only if x minus mu has the same distribution as mu minus x. Now if you know that if two random variables have the same distribution, then expected value of hx would be same as expected value of hy, provided x and y have the same distribution. So that means expected value of x minus mu would be same as expected value of mu minus x, provided expected value of x exists. Now I simplify this. This gives me expected value of x is equal to mu. So this would happen provided expected value of x exists. If expected value of x does not exist, so then anyway this does not make any sense. So we cannot conclude this. Now the B part I have to show if distribution of x is symmetric about mu, then this would hold. So let us try to see how this happens. Distribution of x is symmetric about mu. So by part B, fx mu plus x plus fx mu minus x minus 1 would be same as 1 for every x belonging to R. So I take x equal to 0. X equal to 0 gives me fx mu plus fx mu minus, so it would be same as 1. But I know that fx mu minus is always less than or equal to fx mu. So when I put fx mu is greater than or equal to fx mu minus, I get this quantity is greater than or equal to 2 times fx mu minus, or in other words fx mu minus is less than or equal to half. So you get this quantity. If I put the quantity this fx mu minus is less than or equal to fx mu, then you get this quantity less than or equal to 2 times fx mu, or fx mu is greater than or equal to half, and you get this inequality. Now let us prove the last part, which says distribution of if distribution of x is symmetric about mu, then all odd order central movements would be 0. So let us try to see how. X minus mu has the same distribution as mu minus x. So expected value of any function of this would be same as expected value of the corresponding function of mu minus x. So I take that function to be x to power 2m minus 1. So expected value of x minus mu to power 2m minus 1 would be same as expected value of mu minus x to power 2m minus 1, which implies that expected value of x minus mu to power 2m minus 1. I take minus outside over here, so it becomes minus times x minus mu, but minus 1 to power 2m minus 1 become minus, so this becomes minus, and it becomes x below x minus mu to power 2m minus 1. I take this on this side, so I get x below x minus mu to power 2m minus 1 as 0. So if x has a distribution symmetric about mu, then all odd order central movements would be 0. Of course, for such a thing to happen, these movements have to exist. So let us consider the next slide, where we consider an example. So let x be a random variable with PDF given by this. Now one can check fx mu plus x. So if in place of mu plus x you write down, you get 1 upon pi 1 plus x square. If in place of x mu minus x you write down, still you get the same thing. So this all will be same as 1 by pi into 1 upon 1 plus x square. So the two are same. So by the last result, x minus mu would have a same distribution as mu minus x. But here I cannot conclude that expected value of x is same as mu, because expected value of x may not exist. And in fact, we have seen before in one of the examples that for this PDF, the expected value of x does not exist. So this anyway does not make any sense. Now let me give some problems for take home. So suppose x is a random variable having this PDF, so that the distribution of x is symmetric about 0. So what you have to show is fxx is same as fx 0 minus x, which is minus x, which is clearly happening over here. Now if it happens, hence find expected value of x. Does it exist? That is a question, because if it exists, then finding it from here will not be difficult, because expected value of x would be same as expected value of minus x. So expected value of x would be 0. So now let us consider this example where x is a random variable having mg of mxt, which is e to power t square by 2, minus infinity less than t less than infinity, so that x has the same distribution as minus x. So what you need to show is, in this case, mxt has same distribution as m minus xt. If that happens, then clearly you can say that x has the same distribution as minus x. Now you have seen that if distribution of x is symmetric about 0 and movements exist, then expected value of x to the power 2r minus 1 would be 0. All central movements would be 0. Now here mean is 0, so central movement would be same as expected value of x to the power 2r minus 1. Now you can show that all even order movements would be given by this, which one can get by differentiating movement generating function 2r times and taking t is equal to 0. So before I end this module, let me give a summary of the things I will be doing in the next module. Let A be a subset of R, and suppose G is a function from R to R, and let x be a random variable. Now in many situations, probability x belonging to A or expected value of Gx cannot be evaluated precisely. So we cannot get the exact value of probability x belonging to A, or I cannot even get the expected value of Gx. In those situations, it may be desirable to have some kind of approximations for these quantities, because they may be useful. So in next module, we will derive some inequalities for probability x belonging to A for appropriately chosen A, and we will derive certain bounds for expected value of Gx. So this was all for this module. Thank you for your patience and have a great day.